Back in the day, glassblowing was an art form passed down through generations. Today, we're witnessing something equally remarkable, the jetter technology that's revolutionizing how we make those empty glass bottles we see every day. The jetter process begins with what's called the gob, a precisely measured blob of molten glass heated to around 2000 degrees Fahrenheit. Now here's where it gets fascinating, folks. Unlike the old pressing methods your grandfather might remember, the jetter machine uses compressed air jets, hence the name, to form the bottle from the inside out. First, that glowing gob drops into a blank mold where it's shaped into what we call a parison, basically a thick-walled test tube. The machine then shoots a controlled burst of air through a needle-like nozzle, pushing the glass against the mold walls with incredible precision. This creates the bottle's neck and basic shape in just seconds. Next comes the magic of the blow mold stage. The parison transfers to a larger mold, the final bottle shape, where another carefully timed air blast inflates it like a balloon. The glass stretches uniformly, creating those thin, strong walls we need. Temperature control here is critical. Too hot and the bottle sags, too cool and it cracks. What makes jetter technology special is its consistency. These machines can produce up to 400 bottles per minute, each one identical to the last. The whole cycle, from molten glass to finished bottle, takes less than 20 seconds. Modern sensors monitor everything: glass temperature, air pressure, timing sequences. The finished bottles emerge onto a cooling conveyor called a layer, where they're gradually brought down to room temperature over about 2 hours. Rush this, and you'll have bottles shattering on shelves. After cooling, automated inspection systems check every bottle for defects using cameras and lasers, quality control that catches flaws invisible to the human eye. Let me tell you about a small piece of brass that's been at the center of American music for generations. The Bach trumpet mouthpiece. If you played in your high school band or listened to jazz on a summer evening, you've heard its voice. The mouthpiece is where magic begins. Your lips buzz against it, and somehow music happens. But not just any mouthpiece will do. Bach has been the gold standard since the 1920s, and there's a reason why. Each one starts as a solid chunk of brass. Modern CNC lathes spin and carve with incredible precision. We're talking microns here, shaping that critical cup where your embouchure meets metal. The geometry matters enormously. Too shallow and you lose warmth. Too deep and you sacrifice clarity. After machining, skilled craftsmen hand polish each piece until it gleams, then apply silver or gold plating. Now we're talking serious metalwork, friends. The Mannheim Foundry has been casting ship engine blocks for over a century, and what you're seeing here represents the pinnacle of heavy industrial casting. These engine blocks can weigh upward of 80 tons, that's as much as 50 cars combined. It starts with pattern making, where skilled craftsmen create exact wooden or foam replicas of the final engine block, complete with cooling channels, cylinder bores, and mounting points. The foundry uses a sand casting process, but don't let sand fool you. This isn't beach sand. It's a specially formulated mixture of silica, clay binders, and additives that can withstand temperatures exceeding 600 degrees Fahrenheit. Workers pack this sand around the pattern in massive steel flasks, some standing 20 feet tall. When the pattern is removed, you're left with a perfect cavity. Here's where it gets dramatic. The foundry's electric arc furnaces melt hundreds of tons of steel scrap and iron, refining it to exact specifications. Different ship engines require different alloys. Some need high chromium for corrosion resistance, others need manganese for strength. Metallurgists test the molten metal constantly, adjusting composition right up until pour time. The actual pour is something to behold. Massive crucibles, guided by overhead cranes, tilt slowly to release the glowing metal into the mold. Pour too fast, and you risk air pockets. Too slow, and the metal starts solidifying prematurely. Experienced foundrymen judge this by eye and instinct, even with modern sensors backing them up. After pouring, the casting cools for days, sometimes a full week for the largest blocks. Rush this, and internal stresses will crack the casting. Once cooled, workers break away the sand mold to reveal the rough engine block, still bearing the texture of the sand on its surface. Then comes machining. Massive CNC machines bore cylinder holes to tolerances of a few thousandths of an inch. Water jacket passages are cleaned, mounting surfaces are milled flat, and the block is tested for any hidden defects using ultrasonic and X-ray inspection. The Steerly press brake is Swiss precision applied to heavy steel work. This machine's bending steel plate that's 90 millimeters by 50 millimeters. That's about 3.5 by 2 inches, and at that thickness, you're looking at serious force requirements. Here's how it works. The steel plate is positioned against a back gauge that's accurate to within a hair's width. The machine's hydraulic ram, generating hundreds of tons of pressure, drives a punch down into a V-shaped die below. The steel bends around this punch in one smooth motion. What makes the Steerly special is its computer-controlled back gauge and programmable angle settings. You can store bend sequences for complex parts and repeat them perfectly every time. The operator just loads material, hits start, and the machine executes each bend with remarkable accuracy. This kind of precision bending is critical for shipbuilding, heavy equipment, and structural steelwork, industries that built this country. Springs are everywhere, aren't they? From the pen in your pocket to the suspension on your truck, they're quietly doing work we rarely think about. But making a spring, a really good spring, takes more precision than you might imagine. Modern CNC spring coiling machines are fascinating pieces of equipment. If you've ever tried to wind wire by hand, you know how tricky it is to keep consistent coils. Now imagine doing it with wire that might be thick as a pencil, winding it into springs that need to compress exactly the same way, thousands of times. These machines start with wire fed from large spools. The wire runs through precision guides and rollers that straighten out any kinks, because even the slightest bend affects the final spring's performance. Then comes the magic. Computer-controlled fingers and pins literally sculpt the wire in real time. For compression springs, the kind you'd find in valve assemblies or mechanical keyboards, the machine winds the wire around a mandrel while controlling pitch with incredible accuracy. The computer adjusts tension and positioning dozens of times per second. Tension springs need hooks or loops at the ends, and watching the machine form these is like seeing a metal artist at work. It bends, twists, and cuts, with motions faster than you can follow. Torsion springs, which provide rotational force like in clothespins or clipboards, require the machine to wind the coils tight together, then form legs at precise angles. What used to take a skilled craftsman hours now takes minutes, with repeatability that human hands simply can't match. It's automation done right, not replacing craftsmanship, but extending it. Embroideries come a long way from your grandmother's hand stitching, but the artistry's still there. It's just operating at lightning speed now. The Legia flat embroidery machine represents the cutting edge of textile manufacturing, with multiple heads working simultaneously to create intricate designs. Each embroidery head operates independently, carrying up to 15 different thread colors. The magic happens in the computer control system, which reads digital design files and translates them into thousands of precise needle movements per minute. We're talking 1,000 stitches per minute per head, and with machines sporting 20 or more heads, that's production capacity that was unimaginable a generation ago. The machine uses a pantograph system. Remember those drawing toys that copied images? Same principle, but with servo motors controlling X and Y axis movements to fractions of a millimeter. The fabric stretches across frames that move in perfect coordination beneath the needles, creating everything from company logos to detailed artwork. What's remarkable is the thread tension control. Too tight and you pucker the fabric, too loose and stitches fall apart. These machines automatically adjust tension based on fabric type, stitch density, and speed. Modern embroidery shops can fulfill orders in hours that once took days, but each piece still carries that handcrafted quality we remember from the old days.